Maybe as we're getting ready, whoever had that one question, burning question, can just ask it. I think I saw his hand over there.
For the speaker is talk about and I think questions about and you mentioned about in the media HX or and that's one whether you're using industrial version or just commercial version.
With definitely the industrial version.
Okay. Do you have like some radiation performance already planned?
We're more biased towards actually testing in space because we do have we're implementation partners with the International Space Station National Lab, so we can fly these payloads. We also have some other opportunities because it has been my experience, what you get in the labs and what you get in flight is two different things. And it really has been shown to do that. I flew a Macintosh on a space shuttle in 1992 when NASA swore to me it would never work. So we're much more about flight testing than we are, because I actually think right now we have some methodological deficiencies in how we do radiation testing on the ground.
I have a question for Brian. So if I understood you correctly on your 10th iteration of your vehicle, so what kind of program management and company culture are you fostering to do that?
It is very much a very agile, iterative, small teams moving very quickly. And a lot of the early rovers would just sort of figure out what sort of design would work, you know. And but it's a small team and we work very quickly, and we're definitely focused on iterative design and running tests in the real world.
How formal?
Not formal at all. Basically, people. So I mean, one of the key things that I think is good about Starpath is the idea that it's very much an ownership-based management system. So for each system, you have one engineer who's responsible for that system and who's empowered to make all the decisions for that. So for example, I own the autonomy system. We have another lead engineer who owns the rover hardware. We have another lead engineer who owns the avionics system. And the idea that you don't have to go through layers of bureaucracy. You don't have to necessarily achieve consensus. You hire people to trust and basically tell them you're responsible for this system.
That's
Yes, exactly.
Okay, cool. Thanks for all the questions from the audience, and thanks for all the great talks from the speakers. So right now we also have Brice joining us on the panel. So Brice Howard is the founder of Syntric Solutions, where he advises on robotic autonomy and in-space logistics. He previously developed flight hardware at Bigelow Aerospace and NASA JSC, and led the safer jetpack redesign for the ISS and helped build NASA's Valkyrie robot. So we have him on the panel, and we're very grateful for that. So he will also be giving a keynote tomorrow. So we'll kind of start off with some questions right now, and then afterwards we can get some questions from the audience. So the first one we can touch base on is, I mean, I think we have a very diverse group of panelists here. So maybe if you can go one-on-one and say what unique challenges that robotic systems face on the moon compared to the Earth and how we're addressing them. So I know you talked about GPS and other things. And then I think there was another talk about the dust on the sensors. So maybe you can expand on what the greatest challenge you see on the transfer from the robot systems on Earth versus the ones on Mars or the moon. So we have Rob here on the panel as well. He's joining virtually, but maybe we can go from left to right. So Grace, you can start.
Yeah, sure. Very good question. I can think about the following aspects. First of all, there's a lack of infrastructure, although it's really nice. Like there's a lunar net building GPS, and there's also they were trying to set up Wi-Fi on the moon. I believe it was a Nokia, like a 5G transceiver. It was on the Intuitive 2 mission. And then, so that's the first part, is a lack of infrastructure. And then second part is about the lunar environment is very different. For example, on Earth, we have autonomous driving, right? We can already do some like using like vision-based navigation. and then it could work really well. However, on the moon, thanks. Yeah, the first about the lack of infrastructure, and second, okay.
Sorry.
Okay, so the first aspect is a lack of infrastructure, and then the second aspect is that the moon environment is different from the Earth. For example, there's a lot of interest about the South Pole area of the moon, right? And then because it has a lot of long shadows, just the off-the-shelf like computer vision algorithm that would work for the Earth applications for, say, autonomous driving, it just wouldn't work on the moon. And then the third aspect is lack of data. So if you want to use AI and machine learning, right, you need a lot of data. You need ground truth data for training. And then on Earth, for example, I always compare with autonomous driving, right? There are like millions and millions of miles of driving data available. On the moon, you just don't have that much of data, and that also poses some challenges. I'll stop here.
No, I agree with Grace on that very much, but worked this a very long time with many generations of the lunar explorers. I think right now we have an architectural issue. Everybody's going to the South Pole because they're going, well, we're going to the South Pole because that's where the water is. Well, the South Pole began with my friend Paul Sputis, who's no longer with us, going there for the science. And I've written some papers on this. You can find it out there. The lunar North Pole for industrial activity is far superior to the South Pole. And a lot of the autonomous driving problems, or a lot of the terrain problems, or slaying, if you want to use it correctly, are specifically associated to the really sucky terrain in the south, which is actually the rim of the South Pole Aitken Basin. If you take a look at the area what's called Whipple, and then the bottom of Peary Crater, there's hundreds and hundreds of micro PSRs across an almost flat 110 kilometer distance. And if you actually run the numbers, if you look at the different terrain, all of that there, and we are gaining consensus in Dr. Sam Lawrence at NASA JSC, Dr. Clive Neal from Notre Dame, we're very much pushing for the lunar North Pole because of ISRU and because the water content, especially in Peary, is better. DARPA just started this thing with Lunar Lasso. We still don't know what the extent of the water is. But the recent South Korean data that's not published yet shows that Shoemaker is probably dry. And why in the world would you want to drive into the bottom of a 7-kilometer crater anyway to get water? And so architecture, power. I love the power tower. We designed one way back in 2003. We need power. We need more power. We need one of our things is megawatts on the moon. We need megawatts. If we're going to get the kind of things to be able to refuel Starship, we need megawatts. And I don't think we're going to get there with lunar water. I know the data enough that it's doubtful. So we're going to have to use other methodologies for recovering water, not water, but oxygen on the moon from the regolith, Highlands regolith, doing different methodologies. And we need to start working on these now.
So I think one of the biggest challenges is long-range navigation without GPS, as Grace pointed out, since most outdoor navigation for autonomous vehicles on Earth makes extensive use of GPS to gain an absolute position. So we're going to have to navigate over multiple kilometers using a combination of hopefully good estimations of the absolute orientation from the star tracker, but with relative estimations of translation based on odometry, primarily, I think, laser and vision odometry. Another big challenge is the fact that you have so much slip due to the regoliths. So that hurts you as far as the wheel odometry goes. We're also looking at a goal of navigating very quickly. Like operationally, we want to be able to navigate at 5 meters a second, which is much faster than any existing rover. And a challenge there is both the stopping time of the rover in lunar gravity on regolith, which can be tens of meters, and the limitations of range sensors such as LiDARs, and the need to qualify those sensors to operate in a lunar environment. So those are the big navigation challenges that I see us approaching. There are other challenges in areas which I'm less familiar with, but other people at Starpath are focusing on, such as the plant challenges and the tower challenges as well.
All right, I'm going to take a slightly different, can you hear me on this? All right, slightly different take on it. I think we have a perception problem, not the robot perception problem. I think we have a global perception problem. What is the current state of robotics? What is difficult and what is easy? Right? We all see the Boston Dynamics boxes. You can talk about I need to go do some development work to put a robot in space. Like it's done, right? I think you see the robot, it's like doing backflips. And kind of a theme we had throughout the day has been we need to test a lot, but in order to get that testing, you need funding, and in order to get that funding, you have to get the perception to where people understand that this is something that needs to be developed, in my opinion. And so, like for the last 2 years, I've been building an in-space robotics company, and I've talked to just tons and tons of both on the non-diluted fund and the venture capital side, and there's just a lack of understanding of how big of a task this is. You listen to all the panelists today, right? It's a list of technical challenges. And we won't even be able to get to those technical challenges unless we have the conversation about the funding to get there. And here's the big wake-up call. It's not going to be funded by the government. We have to create an actual economic system. And sitting in a room saying, I believe that we're going to need to go do this, and I believe we need to do that is great. It's fun. It's a good exercise for people that are interested in those topics. But if you really want to bridge the gap, we need to understand how can we make money? How can we actually make money by leveraging the moon or our orbit for other resources? And once we start providing that kind of marketing campaign to the people that actually can fund these, not the government, then you'll see this entire industry take off. I don't think it's actually technology problem.
Yeah, I would say that I think it's ultimately going to be private capital that funds this, even though I think we can also get assistance from NASA and the government, but it's ultimately going to be private industry.
Absolutely agree.
Okay, cool. So I think Rob still is going to be answering this question. He's on the Zoom online.
Okay, let me address technical and business. Here's the thing. We don't need to have an expensive space program like we have today. It's completely biased towards human spaceflight. If we use robotics, the price of space exploration goes down by an order of magnitude or more. So the first thing we have to do is use more robots. Humans have a role in space, but it's not in the infrastructure, construction, industrial environment. It's a bad environment for humans. So first of all, we have to double down on robotics. But the second thing is if you build a robot and it fails, your investors are going to lose interest very, very quickly. So we are under a false paradigm that robots are really good and they work all the time. They will break within a month of arriving on the moon. And unless your design philosophy has a repair and maintenance strategy, predictive repair and after the fact repair, and a modular component architecture so that you can rapidly take a unit offline, repair it, and put it back online, your investors are going to lose interest because robots are failing. When the CLIPS program has a track record of 1 in 4, it's not a very good track record. So we have to reshift our focus on more resilient designs so that we have to expect failure. Don't try to design failure out. Expect failure, but try to design in rapid recovery. If your production line goes down and your investors lose interest, this whole thing will never happen. So our responsibility is to change our design philosophy.
Okay, thanks so much, Rob. So we can have some questions from the audience now. Yeah, yes, Roshan.
I sort of follow up on some of those comments that you made. So you mentioned that test is really, right? You kind of, Horatio kind of alluded to like the lack of data, right? But I'm just wondering, what are your all's thoughts on infrastructure and facility for building new technologies, right? You think that there's a gap in that? And if so, do you think there should be a call to action around this? I say this being, I'm actually on flight mission, and I spent 6 months building a lab, test out perception, right? I'm sure you've done the same thing for what you're doing. So I'm wondering if you think that's a gap that should give some kind of call to action around that. Strongly in general.
I mean, yeah, I think there's definitely a gap. I mean, one of the areas that we're currently looking at is where we want to actually test the outdoor navigation for our rover, and we're looking at various desert test sites. I think having an area that we could test navigation algorithms in the real world in terrain that's at least somewhat similar to the moon or similar to Mars would be very helpful, especially over a larger scale.
Like Rock Mesa.
Could be, yeah.
Yeah, well, I agree, and I think we're being misled by some of the test facilities we have. The Firefly mission, and look, I love Phil Metzger to death. He's a good friend, but I think the regolith problem is being overstated. If you take a look, and I watched it live as a 12-year-old, the Apollo rovers on the moon, lunar dust is strictly dynamic. I mean, it's strictly a displacement problem, and that regolith will go, it's just going to do an arc and it's going to land. It's not as much of an issue as we're building it. If you watch a Firefly landing really closely, and Phil disagrees with this, you'll see that regolith doing a ballistic trajectory and landing. And that's what you're going to see when you're dumping regolith from your box to here. And there's so many areas where, and we need to keep this in our worldview, the differences in the test setups between the Earth and the actual moon. This is why I'm a strong advocate of test in place there, although we've got a test on the ground too.
Yeah, I agree that testing and validation is very important. However, in addition to that, I believe a simulation is just equally important. For example, based on, I don't know if this is on, yes. Based on our participation in the Lunar Autonomy Challenge, right? And they have a really nice high fidelity simulation environment. And for that, we can quickly try and then implement different that navigation, localization algorithms. And then I think that's very beneficial as well.
So I think there's you got to kind of break the problem down into what you're testing and what the value of that test is and how much you're spending on that test. So there's a lot of challenges on the moon. The very first one that I find a lot of young engineers overlook is like having hardware in space is hard. And they just say, oh, you know, people know how to do that. I'm just going to worry about the logistics on the moon. That's probably not one we want to overlook. And so there's a lot of things you can do just in orbit. From testing your electronics, which is a big one, thermal extreme, then upsets. There's a whole lot there. So I think here on Earth, there's things you can do, but there's also low Earth orbit, and I think the testing is about to come down. There's a lot of fear that when ISS National Lab goes away, that we'll lose a lot of payload.
We're going to.
I think there's going to be a stuff that I can't talk about, an onslaught of people that will be offering payload, hosted payloads, and actually I think we're going to have a lower cost access to testing on orbit. And there's things on orbit you can do from just the equipment itself, like if I've got robotics and I need to get it to move in a reduced gravity environment, I can learn a tremendous amount from that. I can learn a whole lot about how I can navigate in the stars, which is a great option for navigating on the moon. So then when you get to, okay, I need to be able to navigate, I'm on the moon. Now we get back to things we can do on Earth. We can figure out how to do waypoint navigation, but probably the best analog here on Earth for testing robotics on the moon is mining specifically inside the mountain. I've had the privilege of helping open up Oak Dam in Australia, where they want to do a completely humanless entry mine. And so we've rethought, how are you going to go and get into these places, navigate, right? You can't have just a wide area network that's going to go through all the, so now you have to go and figure out these problems for reduced comm, reduced nav. How is it going to go map out, extract something? and bring it back. And you know what the answer comes down to every single time is maybe we figure out how we can remote control it before we figure out the autonomy. So autonomy in a place that's already hard to access, that's already not very well known, is a challenge that is ginormous when we have a lot of skills we can do through remote operations. And I mean, we've done robots underwater, right? And they have a pretty high latency lag time, but we're able to make millions of dollars a year with a working economic structure with a lag time. We can probably tolerate that lag time, 2.3-second lag time to the moon and back. So there's still a lot of things we can do by testing here, putting in your lag time to a facility that you're trying to do your navigation with that lag time. Now, when you're there, you're able to kind of accommodate that. I also agree. The regular challenge, my first job at NASA was doing the advanced spacesuit, where we would watch hundreds and hundreds of hours of the astronauts bouncing across the moon and falling over and then getting up, and you get to see the regoliths was not the problem. It's the trying to walk on the Earth that was the problem in that case. So I think the regolith issue is probably overstated based on what I've seen.
Cool. Rob, do you have any thoughts on this?
I didn't, can you repeat the question? It's hard for me to hear it.
So, see if I provide a question, but the question was, there's been a lot of comments and discussion about test. What are your thoughts on the availability of, test infrastructure and facilities on Earth for lunar technologies? And do you think there's a gap? And if so, do you think there should be a call to action to resolve some of those gaps?
In our lab, we have a regolith bin with 120 tons of regolith, and every time we have a question, instead of arguing about it on a whiteboard, we just go in the test bin and try it out. And we save a lot of time and effort just by having that on-demand test capability right there. We also have vacuum chambers, cryogenic dynamometers. Having a flexible test capability lets you answer questions very quickly and iterate more rapidly. So I'm in favor of a lot of testing.
We have time for one more question from the audience, so you did good. Yeah.
Not the south versus the north. If you look at the NASA crater instrument that's on Lunar Reconnaissance Orbiter, you will see that the lunar environment is about 2.5 times more radiation intense than low Earth orbit. Much lower. We used to say 10x. Now, I had a radiation experiment on IM2 that we were going to look at the neutron albedo at the surface from 3 meters above the ground. Unfortunately, ended up on its side in a crater, and so we didn't get that data. But all the indications are, yeah, you have to deal with it, and especially when you're going through the twice a month, when you're going through the magneto pause and going through the different environments and everything. But electronics today is way better than it used to be. And there's several design features that have just intrinsically grown in the semiconductor industry, make them much more robust. Right now here on the Earth, we have more problems from muons than we have from galactic cosmic rays on the lunar surface.
Yeah, you also have, remember, when you're talking about the interaction between the magnetic sphere and outside of the magnetic sphere, the different type of particles. So here, widely be absent of electrons, is mostly going to be a bunch of neutrons that we're worried about. Once you get outside the magnetic sphere, you got a lot more, not only electrons, but photons that are going to hit you. And then you have the back side of the moon versus the front side of the moon, and it's getting a bunch of interactions from the Earth, and then you have the galactic cosmic radiation. None of those are what is going to kill your vehicle. None of it. So I'm going to if you want to actually solve the problem for going to the moon, don't worry about radiation. Worry about the thermal problem.
Yeah. Printed circuit boards don't like 150 degrees C swings. I know, like this.
Okay, cool. You ask your question.
Sure, yeah, nice. So my question's for Dennis. Actually, I've read your book. It was recommended to me by Dr. Michael Lukes from Space Exploration Engineering. And yeah, my question's about the economics of commercial activity. So my name is Matt. I'm a Starpath Vice President of Software. I'm working with Brian on making commercial activity on the moon actually happen. One thing that always needs to be present in conversations about profitability and viability of the commercial industry is launch costs. So, for example, Starpath has developed everything that Brian has presented for single-digit millions of dollars, and our systems are in the tons kind of capacity. Right now, given that the cost of getting to the moon is like between $100,000 and $1 million per kilogram, that means that delivering a ton would be something like $500 million to the surface of the moon. I know you've thought a lot about the viability of different business models in terms of group metals and bringing them back. What are the have you thought in terms of bidirectional launch cost per kilo? What are the thresholds that different business cases become viable at, and what are the first ones that you predict will happen next 5 years?
There is no silver bullet for lunar industrial development. Propellant's not, piping group metals isn't, but we make a decision to put industrial infrastructure on the moon. And my position has evolved a lot in the past 20 years that the greatest resource on the moon may be the vacuum itself. The 10 to the minus 12 torr vacuum that enables you to climb the value chain of industrial product. We have trillions of dollars of GNP that at some point in the development of this or anything else, there's something goes into a vacuum. And on the Earth, those are all batch processes. On the moon, you get 10 to the minus 12 torr for free. And so I think we should think more in that vein. Elon Musk once said that if he found crack cocaine on the moon, he could make money on it, bringing it back. But think about this. This is the one that I've talked about a lot lately. It's silicon-28. The moon's 35% silicon. Right now, super high purity silicon-28 brings about the entire quantum revolution in computing. It is $4 million an ounce for 5.9 silicon-28 right now. 4 million an ounce. What if we drop that by a factor of 10 because we can get it from the moon? That's just one example of how vacuum manufacturing and material science is going to be where the value is built on the moon, using the raw materials, just like we do on the Earth. Mining is a very small part of the overall global GNP, but yet we built that GNP based on what we dig out of the ground.
Thank you.
Cool. Thanks so much for all of your time, and let's all thank the speakers. Okay, this is the end of the session. Thanks so much.